If you work with 3D printing specifically, Fused Deposition Modeling, FDM, the promise of simulation is huge.
Oh, absolutely.
Virtual testing before you waste any time or material. But you also know the pain. Trying to use powerful software like Abaqus to predict stress. It often results in totally unreliable numbers.
Exactly. And for years, the core issue undermining the predictions for, structural integrity was a fundamental lie in the software.
A lie.
A lie. The assumption that the extruded filament is perfectly shaped, a neat little circle or a perfect rectangle. Our source material today confirms that this leads to, catastrophic errors.
So today we're doing a deep dive into a new experimentally validated methodology that actually fixes this flaw.
Right. It gives FDM simulations real engineering-grade precision. We're finally bridging that gap between the G-code and real-world physics.
Okay, so let's break this down. Why does the actual physical reality of printing mess up that idealized virtual geometry so badly?
Because printing is a messy process. I mean, you've got compression, you've got heat, you've got flow.
Right.
The researchers used high-resolution scanning electron microscope analysis, and they confirmed the filament cross-section isn't circular at all. It's an oval rectangular profile.
Oval rectangular.
Yeah. The nozzle literally squishes the material down. The heat lowers the viscosity so it spreads, and then adhesion makes it flatten out. So if you're using the wrong shape in your Abaqus mesh,
your whole prediction is off.
Your ability to predict mechanical anisotropy, how the part's strength changes depending on the load direction, it's guaranteed to fail.
Okay, so if the shape depends on the printer settings, they needed some kind of model to predict how much it squishes based on user inputs.
Yeah.
How did they even begin to handle all those variables?
This is where they brought in the statistical muscle. A Box-Behnken Design of Experiments, or BBD.
BBD, okay.
This method let them correlate 4 key parameters: layer thickness, raster width, extrusion temp, and printing speed to the actual filament dimensions that come out. It's a really complex puzzle.
What's fascinating to me here is the interaction. I'd assume a faster print speed means less squish, but the source says the virtual width actually increases with higher temperature. And this is the weird part, with decreased print speed. Why would slowing down make it wider?
It's all about time. It gives the material, which is, all soft and gooey from the heat, more time to flow sideways and stick to the raster next to it before it pulls down.
That makes sense.
The BBD model gave them these really precise equations for that behavior. And when they checked the error, the virtual thickness was off by only 1.06%.
Wow.
Virtual width was a bit tougher, around 8% error, which just shows you how nonlinear those flow dynamics really are.
That's an amazing model, but it's useless if you can't actually use it, right? You can't just manually draw millions of tiny corrected ovals.
Exactly. The implementation is everything. They developed a custom Python-based interface. This tool is the magic ingredient.
The middleman.
Precisely. It reads the entire G-code toolpath, that's the step-by-step instruction file, and then it uses their new BBD equations to sweep that calibrated oval rectangular cross-section along the whole path.
And that generates the input file for Abaqus.
A perfect mesh-ready input file. It ensures even complex honeycomb or triangular infills are replicated exactly.
All right, this is the moment of truth, of validation. What happened when they tested this corrected simulation against real tensile specimens?
The contrast was it was unbelievable. When they ran the standard non-corrected models, where most people have been doing it for years, they produced catastrophic relative errors. We're talking 7% up to a truly useless 92% error.
92%. Wait, that's not a simulation, that's a coin toss. That makes the whole idea of virtual design totally pointless for structural integrity.
It does, but the corrected model, it just eliminated that. It achieved what they call engineering-grade precision.
Okay, what does that mean in numbers?
It dropped those errors to a range of just 0.03% to 7%. Take the strongest orientation, the 0-degree raster. The corrected model predicted an ultimate tensile strength of 41.4 MPa.
And the real-world test?
The experimental results were between 41.4 and 41.5 MPa. It was a perfect match. Meanwhile, the old model underestimated that same strength by about 15% every single time.
So what does this all mean for you, the person listening? The big achievement here is that this experimentally calibrated model finally captures what's really happening in FDM printing. It lets you do reliable virtual qualification.
It closes a critical loop. We finally have a high-fidelity path from your printer settings straight to a reliable mechanical simulation, but Here's the provocative thought we want to leave you with.
Okay.
The methodology is great. It's broadly applicable, but, and this is a big but, you have to recalibrate that virtual raster model for each new material printer combination.
So it's not a one-time setup.
Not at all. High-fidelity simulation isn't a piece of software you just install. It's a continuous, targeted process tied specifically to the hardware and the actual material you are using at that moment.